Okay, thanks a lot, Andres. Great, so when I was asked if I would come and give a talk, I wondered what I should give a talk about. And I've been working at Facebook for a few years now, and I've been working on this system called Sigma, and I've given several talks about Sigma, so this is one of the talks that I've given in the past. And there are lots of things to talk about. So there's the Haskell framework, there's the applicative do transformation that we have in the compiler, there are garbage collection optimizations, there are war stories about bugs that we found, and lots of cool stuff. But usually in these talks, I have one slide buried at the end somewhere that says something called live updates. And what I observed is that people would come up to me after the talk, and they would ask me questions, and most of the questions would be about this one slide. So that told me two things. It told me, one, people were still awake at the end of the talk, which is quite good. But two, people are really interested somehow in how they can do live updates of their Haskell code. So this talk is going to be all about this one slide, kind of expanded into 100 slides. And I should warn you, it's not going to be all that pretty all the way through. There are some dark corners in there that we're going to get into. So it's probably a good idea that this is after the beer break. You should not be entirely sober for this stuff. So to put things in context, we wrote a blog post about this about a year ago. So this is on my blog. You can go read it. This goes through the process of how you can use hot swapping in your Haskell code. And it talks about some demo code that we put up on GitHub that you can also go and look at. So we kind of just threw this over the wall about a year ago, and it's still there. We have done some updates. I put one of the packages on Hackage lately so that you can at least import one of the APIs using Cabal. OK. So in this talk, what I'm going to talk about is why do we need hot swapping? And that's a question you should ask, because if you don't need hot swapping, you should probably not do it. Think very carefully. I'm going to talk about how it's done, how we do it at scale in Sigma. And if the demo gods are smiling on me, we'll do a demo. Let's hope things are working. And I'm also going to talk about what things can go wrong. So what are the sort of weird and bizarre ways that hot swapping can cause you problems, and how to spot those sort of things and how to avoid them. So I'm going to have to talk a little bit about Sigma, which is the platform where we use this really in anger. So Sigma nowadays is a general purpose platform for deploying Haskell code inside Facebook. So I used to say that Sigma was a rule engine, or it was a spam filtering engine, or something like that. But nowadays we sort of generalize things to the point where you can just ship any code at all on Sigma. So teams inside Facebook, if they want to ship some code, they want to make it available to other services running within our infrastructure, they can just check it into Sigma, and then it will be deployed and usable from anywhere. So right now, it's used mainly for detection of abuse and malicious activity. That's mainly sort of historical. It's also used by various other teams doing other things. To be honest, I don't know all of the different ways that Sigma is being used, because I don't have to be in the loop when somebody adds some code to Sigma. So it's being used in lots of interesting ways. So in these kind of use cases where we're dealing with malicious activity, we're in an adversarial situation where we're trying to stop an attack before it's had too much of an impact. So getting code into production quickly and safely is really important. So Sigma just looks a little bit like this. We've got a service. It's running on lots of machines inside our data centers. And there are some clients, some other service perhaps, some front-end code perhaps. Anything else running in the data center can talk to Sigma by sending a request and getting a response back. So for example, the Facebook front end, when somebody wants to post a message or write a comment or something like that, sends a request to Sigma saying, please classify this activity. And Sigma will run all of the rules it knows about how to, whether to block or allow this content, and return a response back to the front end to say whether to block it. Another example of where Sigma is used, it contains a system called Duckling, which we also open sourced lately. You can go and find Duckling on GitHub. And Duckling does some natural language processing. So you can send a message to Sigma that says, try and find a date or a time in this bit of text. And Duckling will say, sure, if you said, say, a week next Friday, that's the following date. So that's an example of something else that Sigma does. So it sits in the infrastructure, and it talks to lots of different services. It talks to databases, caching services, counters, pretty much anything else that you can talk to from a service inside Facebook, you can talk to from Sigma. And you can even do that without restarting Sigma and rebuilding it. You can talk to just anything else at all. So that's been both a blessing and a curse. It makes it very flexible, but it also means we have dependencies on just about everything. So when something else goes wrong, it tends to have an impact on Sigma. So a central principle of Sigma is that it's compute only. We only do compute. We don't have any state at all. And there are several reasons for that. One is that databases know how to do state a lot better than we do, so we should let them do their job. But it means that it's very easy to scale the service. We can just add more machines. They're the same as all the other machines. It's very resilient. If some machines go down, the other machines will handle the load. And it just makes the whole system very easy to manage. But we can do caching, and we definitely do caching to improve the relationship with the other external services that we're using and not put too much load on them. Okay, in terms of scale, we've got thousands of servers. I have to be a bit vague here, I'm afraid, but there are thousands of servers, hundreds of thousands of lines of code, dozens of teams actually shipping code on the platforms that are writing code against our DSL and shipping changes. And there are something on the order of hundreds of changes per day that we have to deploy on top of Sigma. So why do we have Sigma? Well, the main reason is that anybody can ship code. So that makes teams autonomous. They don't have to worry about building their own services, doing their own deployment, doing their own capacity management, all of that sort of stuff. They can just check their code into Sigma, and we handle all of the deployment and the infrastructure issues for them. So it's very easy to ship some code and make it available to other services to use. So this is a very nice way to build infrastructure. I went to a talk at Strangeloop a couple of weeks ago by somebody at Twitter who was describing a similar system to solve exactly the same problem. So instead of having individual microservices managed by different teams, they just have a single container that manages all of the microservices in one place. So another important thing is that not only can you ship code, but you can ship code fast. So I mentioned earlier that for handling malicious activity and abuse, we want to be able to get code into production very fast. So that's one of Sigma's main values. So the principle that we sort of tell to users is, when you've checked your code in, whatever's in the repository is now running in production. So that's kind of the principle they're working with. Of course, it's not entirely true. There has to be a little bit of delay somewhere, because once they've checked their code in, we have to build it somehow, and we have to get it out to the machine. So there's sort of stuff that has to happen. So there's a delay after they've checked their code in before it's actually running. Not only that, but it also has to type check. So you can't just check anything in, because then we can't ship it. The code in the repo has to be type correct. Otherwise, we can't build it, and if we can't build it, we can't ship it. So kind of what you would like to do is to have the repo be type correct all the time, right? You would like to guarantee that whatever is in the repository is type correct so that you can deploy it. But that gives you kind of a scaling problem. So imagine that this is your repository. This is your master branch here, and we've got a queue of changes, delta 1, delta 2, and delta 3, waiting to be deployed. We can go ahead and type check delta 1 on top of master. And maybe that takes about 10 minutes to type check. Let's just say, for the sake of argument, it takes about 10 minutes. Now we can check that in on top of master, and we can deploy that if we want to. But only once we've done that can we finally type check delta 2, because we don't know for sure that if we had type checked delta 1 against the point where, delta 2 against the point where delta 1 was added to the branch, we don't know whether that would have type checked. So you can only do this in a linear fashion. And if we do this once every 10 minutes, that's not going to be fast enough. So you have this choice. You can either do a high throughput of changes, or you can have a guaranteed type correct repo at all times. You can't have both of these. So the alternative way to do it is to type check all of your changes in parallel. And then if they all type check, then we'll just rebase one on top of the other to get the final repository. And then every time we've checked something in, we can deploy it. So we can deploy any of these individual changes along the way. But now we've got the problem that, well, trunk may break. So let's suppose, for example, one of these changes is removing a function, and another one of these changes is adding a use of that function that was previously unused. So both of these are independently correct changes, but if I combine them, if I rebase them, which will work fine because they were in different parts of the code base. If I rebase one on top of the other, now I've got a problem because the use of the function is referring to something that doesn't exist anymore. So we've got this small possibility that our tree might be broken at some point. And we found that, so we use this method in Sigma, and we found that this doesn't actually happen very often. So you set things up so that if trunk breaks, then alarms go off and people get woken up and all hell breaks loose, but it doesn't actually happen very often. So we find that we don't have to go in and manually fix things when this happens all too often. So how are we going to actually go about deploying these updates? Well, I could build a complete new server, and I could ship the server to all my machines, and I could restart all the servers and start running the new code. That would be the easy way to do it. And for sure, if you can do that, then you should definitely do it. But suppose that your server takes 10 seconds to start up, which it might well do. Imagine your server has to start a Docker image or a container or something like that, and then it has to connect to lots of other services, and it has to download caches and do all sorts of stuff when it starts up. So it could easily take 10 seconds to start up. And you don't want to restart all of the machines at the same time, because then if you do that, your service is completely down for everybody. So you have to do a rolling update, where you restart some of the machines, and then when they're up, you restart the next batch of machines, and so on. So you have to decide how many of your machines you're willing to have down, and say, let's say we choose 10%. So now our rolling update is going to take 100 seconds. And that's putting a limit on how many changes we can have out, we can roll out at any given time. But, well, maybe you could pipeline these things, but then you don't really have much idea of what's running in production. So you would really like your updates to go out as atomically as possible. And in practice, the startup times could easily be a lot longer than that. So 10 seconds is quite conservative. In our case, it takes much longer than 10 seconds. So, and furthermore, restarting all these processes, if they're loading caches from other places, making connections to other services, that puts a lot of load on the other infrastructure around it. So we'd rather not have all that churn going on. So we don't want to have 10% of our servers down all the time. That's quite a lot of servers that we're not using. And we don't really want to build and ship the whole binary and send it to all of our machines, because that's quite a lot of bits to shuffle around. And we really like our updates to be instant across the fleet, because then we can measure the difference more accurately between versions, and we can say when there's a regression happening. So none of these are good. Rolling updates doesn't work very well. Maybe we could use GHCI, because after all, GHCI can incrementally load code as it changes and let you work with that code. But GHCI is much too slow. So it's interpreting everything. We can't use the interpreter for the kind of throughput that we need. But GHCI does have this mechanism for dynamically loading compiled code. When you're using GHCI, you're loading compiled packages into the process. And that's a really useful facility. Maybe we can use that. So let's do hot swapping of compiled Haskell code by linking it into the process. So our server will look like this. We're going to have some server code at the top. So that's the bit of static code that's going to talk to the rest of the world. We'll have lots of libraries at the bottom, again, statically linked into the binary. So these libraries are going to be shared between the server code at the top and a dynamically linked lump of code that we're going to have in the middle. So now, how do we swap this? Well, let's go from version 0 to version 1 of the code that we want to run in our process. And we link that dynamically into the address space. So there's a couple of ways we can do that. We can use GHC's runtime linker. That's the one that GHCI uses. Or we can use the system linker. So there's a kind of interesting trade-off here. GHC's runtime linker is limited to the low 2 gigabytes of the address space. So we recently had to move from using that to using the system linker, which can load stuff anywhere in the address space because scale, things get bigger. So now what happens after you've loaded v1? Well, now the server says, I've loaded v1. I'm going to make all of the requests that I'm serving now use the code that's in the new version of the code that I've loaded. So all new requests are going to be served by the code in v1. But I haven't stopped running the requests that were running on v0. There are still some requests running on v0. We've got lots of concurrent requests going on all the time. But eventually, the requests running on v0, they drain and they finish at some point. And then the garbage collector has a look, and it says, well, nothing is using v0 anymore. I can just remove that from the address space. So the garbage collector, when it does a complete sweep of the heap, discovers that nothing is pointing into v0. And now we can finally unload v0 from the address space. And we've done the complete swap. So this is really good because the server can just stay up continuously serving requests all the time. We can have active requests running on both versions, or even more versions if we want to, simultaneously while we're swapping them. And we switch to a new version without having any downtime at all. So we can do a simultaneous update across the entire fleet. And there's no need for a rolling restart. OK, so maybe you've heard that hot swapping is hard. I just made it look a bit easy. But there are lots of things that can go wrong. So let's see. Well, so we've got a couple of APIs that we have to worry about here. The first API is at the top. So this API is used by the server code. So the server code has baked into it the API that it's going to expect the dynamically loaded, I'll call this the shared object. The dynamically loaded shared object, the API that has to expose, must be the same every time. OK, so that has to be fixed. The APIs at the bottom, there are lots of library APIs. So the dynamically linked code can call any of the libraries that were linked into the binary as you shipped it, so the server that you shipped. So we make sure that we link in a whole bunch of libraries that you might need into the server, and we make sure we link the whole lot, not just the bits that the server is using. So you link the whole lot just in case the dynamically linked code needs it. So changing APIs becomes a bit tricky. So if you have a single server, you can change any API within that server just by changing it and recompiling and shipping it. But now we've got a sort of a versioning situation where if you want to change an API, suppose you want to change a library API, we can add a new API, and now we can update the server, and the server now exposes the new API, and only then can we start using it from the dynamically linked code. And then once we've made sure that we're past a certain version of the dynamically linked code, now the old API isn't being used anymore, so we can delete the old API. It doesn't disappear until we've finally updated the server. So this whole process takes about 2 weeks. And when I was writing this slide, I was thinking, 2 weeks, that's terrible, right? But in the GHC world, it takes 18 months to change an API, so this is perhaps not too bad. I'm a bit spoiled by living in a closed world sometimes. So APIs is something you have to be a little bit careful about. And because of this, what we found is that there's an incentive to try and move things into the dynamically linked bit of your binary. Because once things get into this bit here, they're really easy to change. You can just check in some code, and now it gets deployed everywhere. You don't have to update the server or wait for any other team to work on it. So we found that code sort of naturally migrates out of the libraries and into the shared object. And over time, we found that all of the libraries that we originally had in the server tended to move into the dynamically linked code. So all we're left with, actually, is just standard third-party hackage and stackage libraries and C++ code that lives in the server. And this is really great, because it gets the platform team who are responsible for that server code, they're just completely out of the loop now. So the people who are working on the shared object, which is many teams, so they are now empowered to change any of these libraries. So that was APIs. What else can go wrong? Well, I'm going to mention state. State is always a problem, right? What about state that lives across a hot swap? So imagine that you've got some state so this is v0 here. So our state type, let's see, it has a couple of things in it. And maybe in v1, we change the state. We remove one of the fields of the state. So what will go wrong? Well, if we have any values of this state floating around when we load v1, and v1 gets to see a value of this state and assumes that it's a value of this state type, then it will go horribly wrong because it's the wrong size. We'll get a crash or a seg fault or something. So you can't have types that change where you're propagating values from the old type to code that assumes the new type. So in fact, migrating code where state types change is a research problem. You can go and find lots of interesting papers about it. But our solution to this is just to say, no, you can't do that. Right? So we're going to keep the problem really simple and say there's no persistent state. You can't possibly have any values of a type that's defined in one version of the shared library and is used by the next version of the shared library. And we enforce this by APIs, basically. The APIs that you are allowed to use in the business logic in the shared library are of a form where you can't possibly manage state that lives across multiple versions. And this is easy to enforce. We have a type functional language here, so we can make sure that things are just functions and they don't manipulate state. But I did say the server has caches and stuff, so there is some state going on somewhere. So where does that state show up? Well, this is one of the main APIs that people using our system write with. So this is a policy. So a policy is going to implement one of those things that says either block or allow a particular type of content. So a policy has the type, well, it's in a Haskell monad and it returns some responses. The Haskell monad gives you access to some input. So the input is per request stuff. Anything that comes in from the request is stashed in the monad, and then you can get access to it from anywhere. Why is it not an argument to the function? Well, it turns out that memoization works a lot better if you have it stashed in the monad. So Haskell also gives you parallel data fetching, lots of caching stuff, but it doesn't let you do arbitrary I/O, and it doesn't let you do side effects. And these things give us nice properties that let us automatically memoize and share things and cache lots of stuff. But you want to have some effect. So the effect is in the thing that you return in the responses. So the responses can say, either block this action, but it can also say, write something to a database, or cache the following thing, or increment a counter somewhere, or something like that. So all of the side effects of a policy are sort of explicit values of the responses type. So you can return your side effects, but you can't do them, and you can't look at their result afterwards. So there is state. But the state is not something that you can use from the user code. The state sort of lives at the bottom. It's in the caches, in the databases, in the way that we're talking to other services, in the libraries that you're using from the user code. So what this means in practical terms is that the state types must live down here. The state types can't live here because then they might change from one version to another. So the state types all have to live down here. And that ensures that when we swap a shared library, the state is still a valid instance of the type, of the state type. Okay, so I'm going to show you a bit of our hot swapping library, our demo library, which is on GitHub. So it consists of 4 packages, of which one of them, so the GHC hot swap package, that's just a library that you can use. You can import that from Hackage. So what are these other ones? Well, remember I said that the API between the server code and the dynamically linked code has to be completely static. It can't change from one version to another. So that's what's embodied by the GHC hot swap types, package. So this is just an example. This is not a package you would use. It just shows you how to do it. So the types module in this package gives you the types of that, the API that must remain static between the server code and the dynamically linked code. And then we've got a main module for our program. It's going to be the demo. I'll show you that shortly. And in the GHC hot swap SO for shared object package, there's a couple of modules. So one is my code. That's the code that you're going to modify, the code that you're trying to export and link dynamically. And there's a bit of boilerplate that we call so.handles. That's the bit that exports the API across the boundary back to the server. Okay, so my code is the bit that we're going to change. So how do we define this API? Well, we're going to define a data type. Let's call it SO exports. And this is a record of functions. And these are all the functions that we're going to export from our shared object to the code that uses it. So for example, we might have a my function that takes a string argument and it's an IO operation. This is a function that we're going to export, again, from the shared object to the code that uses it. So now we have to get that from the shared object somehow across that boundary. Well, we could export it as a Haskell function, but that means the server code has to understand how Haskell functions are compiled and what their generated names are and that sort of thing. So that's a bit too low level, a bit too dependent on the compiler version. So what we do instead is that we foreign export a function that I've called hsMySO function here. So when you foreign export a function, that's saying I want to put a function called this in the object code, and it will be called exactly that, and this is its signature. So it's a C function, but you can guarantee that it has this symbol name, and you can guarantee that it has this type. And what's it going to do? Well, when I run it, it will return a stable pointer pointing to this record of functions up here. So even though my API might have lots and lots of functions in it, I only need to do this once. This is going to return a stable pointer to the record of all the functions, okay? So that's how I foreign export it. And what do I foreign export? Well, it's this handle here that makes a new stable pointer of the SO exports. And this is the instance of SO exports, where I'm actually going to build the record that has the fields that point to the actual functions that I want to export. Okay, so far? Cool. So how do you actually use that? Well, this is the main program. So the main program is going to say, well, first of all, I call this function register hot swap, and I pass it the name of that foreign exported function that's going to return my record of functions, and I pass it the file name to the object file to load, and that returns me a myData thing, which is, that's an abstract type. I'll show you a bit more about that in a minute. And the abstract type supports a couple of operations. One of them is with SO. So with SO, when given this myData, gives you back the record. So register hot swap has loaded the code into memory. With SO is grabbing that record of functions across the boundary and giving you the record of functions so you can then call them. Okay, that's half the story. So later on, I want to swap in a new version of the code. So I say swap SO with the myData handle, and I pass it the new file path to the new version of the object. And now, again, I can use with SO, and I can use the new version. All right, that's pretty much the whole API that I've shown you there. Cool. So here it is again. The updatable SO is the abstract type that you get back from register hot swap. So register hot swap takes a string, which is the name of the symbol. It takes a file path pointing to the object file, and it returns you an updatable SO parameterized by the type, the record of functions. What's checking that you get this type right? Absolutely nothing at all, right? Don't screw up. And then once you've got an updatable SO, then you can call with SO on this, and you give it a function that takes the record of functions, and it's an IO operation, and it wraps that. So again, what's checking that you don't leak this from this function? Nothing at all. I'll tell you what goes wrong if you do that in a minute. And swap SO is the thing that I showed you before. Let's see if the demo is working. So for my demo, this is my function that I'm going to export from my shared object. It's a function that takes 2 chars and returns a char. And I'm going to make it delay for a random time between 5 and 10 seconds. So that's just to sort of simulate the effect of a request that might take some time and finish at a non-determinate time in the future. And then I'm going to return either X or Y. In the first version, I'm going to return X. So that's my code in the shared object. Oops. So let's have a look at the main module. So let's look at this function looper first. So looper is going to be a thing that repeatedly makes requests or simulates requests using code in the shared object. So it's going to take the shared object, it's going to take a couple of counters that I'm going to use to be able to observe what's going on. And it goes around in a loop forever, and then it does this with SO to get access to the functions. And then it calls a function from, I think I changed the name. It's called sum function. This is the thing that I've just shown you. So this takes 2 chars, and it returns an x. And depending on whether x was A or something else, I'm going to increment either counter A or counter B. So that will let me observe which version of the shared object I'm using. Yes?
That's the interface that doesn't change.
Yes, that's right. Yes. The question was, SO exports is the interface that doesn't change, and the answer is yes. OK, so in the main function, well, I'm going to take the path name of the first object to load as my argument. And then I'm going to start up a thing called EKG, which is a nice little way to monitor your program in a web browser. I'll show you that in a minute. I'm going to make 2 counters that I use with EKG, counter A and counter B. So now I'm going to register the shared object using this. That's the name of the symbol. And I get back an SO. So now I'm going to perform a garbage collection every 1 second, every second. And the reason for that is that the garbage collector is the thing that unloads the object. So I'm going to show you that the object actually gets unloaded. But to make sure that happens, I need to ensure that the garbage collector runs often enough. So that's what that's doing. So now I'll create 1,000 threads, and the 1,000 threads are all going to call that looper function that I just showed you. So we're going to have 1,000 threads repeatedly calling into the shared object. And each one of those, every time we call in, it will wait between 5 and 10 seconds and then increment either counter A or counter B. While that's happening, we'll ask the user to type in the path of the next shared object to load. And once they've typed one in, we're going to swap it. And meanwhile, these threads are all still running, performing requests. So after I've swapped it, the with SO that I showed you up above, that's going to be swapping to using the next version of the shared object. All right. So I've made a couple of scripts. So I'm first going to say, let's build the first version of the shared object. So that's built it and called it a.so. So now let's say let's run the demo program. Oh, I forgot something. So I have to give it the name of the first shared object. All right, and that's started, and it's asking me for the next file name of the next shared object to use. So let's have a look in our web browser. Hopefully this is going to work. So EKG is this very nice little monitoring thing that lets you connect to your Haskell program in a web browser, and it shows you things like how much memory it's using. And it can also show arbitrary counters. So I've got counter A, which I'll add here, and counter B. So this is the graph for counter A at the top, and this is the graph for counter B at the bottom. So you can see that counter A is spiking around a lot because randomness. But you can see there's definitely events happening on counter A, and there's nothing happening on counter B. So now I want to change my code. So let's come over here, and let's go to my code. And instead of returning X, we're going to return Y here. And let's build it. We call it b.so. So now I have to go over here and tell the program to use b.so. So that's done that. And now let's see what happens to our counters. So you can see that counter A sort of gradually tailed off and counter B gradually ramped up. And now we've completely swapped over. So so the idea here was to try and demonstrate that the requests running on counter A were running at the same time as the ones on counter B as we swapped over. So counter A sort of gradually drained. and then we've completed the swap. So I can show you, just to give you a bit more evidence. Let's see here. So I can look at the memory map of the process and grep through it for my shared objects, just to prove that, maybe you can't see this. So here we go. So I grepped through the memory map of the process just to see which objects are loaded, and it showed me that, well, b.so is currently loaded. So actually, let's go back and let's load A again. And when we've done that, let's have a look at our memory map. Now it says B and A are both loaded. And we've got the ramp up as before, and it's swapped over. So now if I grep again, oh, now I've only got A loaded. So A and B were sort of briefly loaded for about 5 or 10 seconds, and then it managed to unload it. So it worked. Yeah, good. Right, so what about unloading code? So I told you that the garbage collector gets involved. So we have to understand a bit about how the pointers are, how the pointers between the GHC heap and the various versions of the code are represented. So let's imagine that we've got two versions of our shared object, v0 and v1. And while requests are running, there are pointers from objects in the heap, in the GHC heap, that point into the code. Why do you have pointers from the heap into the code? Well, if you have thunks, for example, unevaluated objects, so thunks are a reference to some code to evaluate the thing. So if you have a thunk in the heap over here, it's going to point to something in the shared object. And if you have some data of a particular type that's defined in that shared object, then again, the data will refer to the code that represents that data type in the object. So that's how we get pointers from the heap into the object. We might also have pointers going the other way. So if you have a top-level definition, a top-level, we call them CAFs, constant applicative forms. So something of the form x equals expression, where it's not a function. Then when x is evaluated, the value for x lives in the heap, and the location where x, where the symbol for x is in the shared object, will have a pointer from there into its value, into the heap. So that's how we get pointers going the other way. So now v1 is in memory. The server says, all the requests should go to v1 from now on. And eventually, the requests drain on v0. And the server says, oh, I finished with v0 now. No more requests are running. You can go ahead and unload it if you want to. And the garbage collector looks at the heap, and it says, oh, there are no more pointers into this object, so I can unload it. That's what should happen. But maybe you're wondering, why is a GC involved at all? Why don't I just, as soon as I know that there are no more requests running on v0, why don't I just say, let's delete that from the address space? Well, you could do that if you were really sure that you'd done it right. But the GC is an extra layer of safety. So if the program said unload v0 a little bit too early, then the GC is the safety net that prevents that from crashing the program. And the other thing that can go wrong is if you accidentally leak some memory, leak some data that's referring to the old version of the shared object, then again, we don't crash in that case. Well, you'll probably crash eventually, because if you keep on loading new versions, eventually they'll fill up the memory. And the garbage collector has more work to do when you're trying to unload things, because it has to check all of the pointers in the heap to see whether they refer to anything in your shared object. So you're going to crash eventually, whether it's because of extra GC load or running out of memory. Bad things will happen, but not as fast as they would have done if you just deleted it. So how can leaks arise? Well, you might think in principle, if we finished all the computation, right, and I told you these things are just functions, they don't have any state, we're not keeping any of the results anywhere, then there shouldn't be any live references to the code left, right? That makes sense. But one thing that we found actually happened quite a lot was that a thread can get deadlocked. So you have one request that's supposed to have finished, but actually it got into some horrible deadlock situation. Maybe it was a bug in the library somewhere, or maybe the server it was waiting for didn't respond and the timeout wasn't working or something. Anyway, you get a deadlocked thread. And that, because that thread is referring to all sorts of stuff from the code that it was running on, that prevents the code from unloading. So that doesn't necessarily invalidate our assumption on the previous slide, because this is just really a case of the computation hasn't finished yet. It's never going to finish, but it hasn't finished yet. So these are just bugs that you have to fix. Another kind of problem is persistent state leaks. But you said that can't happen. You're right. But so the state lives down here, right? So that means we can't have state that refers to a shared object. But what happens if you mutate the state? What happens if the state is some kind of mutable thing and you write something into it that refers to something in your shared object? So here's an example. Imagine your state contains something like, well, I want to keep some statistics about requests. Maybe I have a map from request type to stats about that request. That's a perfectly reasonable thing to do. You might want to keep information about what's been happening on the server so you can aggregate the results somewhere and use that for optimization. So that's reasonable, but this is a mutable thing, an envar. So if we add something to this map, and perhaps we don't evaluate it far enough, perhaps it has a thunk in it, then that thunk is going to refer to code in our shared object, and now we've got a leak. So that can happen. Or maybe you have a cache. Maybe you have a mutable map from request type to results of some kind, so that you can shortcut some particular types of requests. That's another reasonable thing to want to do. But again, if the stuff that you're writing into here isn't fully evaluated enough, or perhaps it contains types that are defined in your shared object, now you've got a leak. So these things actually happen for real. The instances of these things really were a problem that we had to go and debug. And how does it manifest? Well, the server's running out of memory. GC is getting slower. You have to sort of notice that by watching your metrics on your dashboard or something. And then you can go in, you can attach the debugger, and you can try and sort of dig around in the heap and try and find out what's going on. This is a really laborious process. I said things were going to get messy, and they do. So how do you go about fixing this? Well, first of all, don't mutate the state, unless you really have to. And if you have to, stare at the code that mutates the state very, very hard, and then stare at it some more. And make sure that none of the types that you're storing in that state are defined in the shared object. Well, how could that happen? Well, maybe if you're using dynamic types or you have existentials or something like that, you can embed types that are defined in the shared object in the shared state. Once you've done that, sort of deep C can compact all of the data so that it doesn't have any thunks and it definitely doesn't refer to any of the code in your object. Okay, so I'm just going to talk a little bit about, that was all about the nitty-gritty of hot swapping. But when you're deploying code really fast, you need to have some kind of confidence that the code you're deploying is not going to completely destroy the world. So how do we ensure safety and reliability? Well, we've already got a head start. So we already had strong types and purity, and we have an EDSL that prevents you from doing side effects, so that's one way that you can't screw up. The EDSL also enforces a nice isolation between different request types, because the request types can't interact via any kind of state or side effects. And we've also added fixed limits on time and the amount of memory allocation that every request can do, because it turns out that sometimes people commit infinite loops to the code, and that causes all sorts of problems unless you actually put limits on the amount of time things can take. So those are sort of things that stop disasters from happening or limit the damage a disaster can do. But you can't rely on all of these things. There are still lots of stuff that can go wrong. So for example, somebody might commit some code that causes a large performance regression. And now all of a sudden you need 20% more machines than you needed before. And now I'm going to stop serving all of my requests because I don't have enough machines. Or maybe you introduce a large functionality regression. Perhaps in the case of abuse detection, maybe you have lots more false positives than you had before, or lots more false negatives. Both of those things are bad. And we'd like to know about that before we commit the code. Or maybe the new version that you committed causes some kind of catastrophic failure because it exercises a bug that wasn't being exercised before and causes the server to crash. So you'd like to know about these things before they cause too much damage. So one thing that we found really useful is a system called experiments. So when you make a change to the code, and you put up the code for code review, as we do with all of our code, what we do is we have an automated system that goes and builds a version of the shared object with your code, and then sends a bunch of simulated client traffic against that version, and measures the results. And it will tell you things like, oh, the change that you're about to make regresses performance for this one request type by a certain percent, or it will need so many more machines if you commit it. Or maybe your change increases the number of exceptions, and it causes lots more failures to happen than were happening before. Or maybe it increases the number of responses, so it blocks a lot more stuff than was being blocked before, or it doesn't block as many things as were being blocked before. So all of these things catch lots of problems before they actually make it into production, which is great. But that's not all. It turns out that sometimes bad things still get through, so we have a last resort that we call the push train. So if you imagine that the series of changes that we're trying to deploy to the service, Delta 1, Delta 2, Delta 3, Delta 4, they're sort of going to be deployed in order. But we're not going to deploy them to the entire fleet at the same time. Let's say we divide our fleet into a staging phase, which is 10% of machines, and then the rest of the fleet, the other 90%. So this train is going to live in the staging phase, let's say for 10 minutes. So a change first gets deployed to staging, and then the train moves through staging, and eventually, if it survives, then that change goes out to the other 90% of the machines. So the idea of this is that we can monitor what's going on with that 10% of machines and compare it against the other 90%. And if really bad things are happening, then we don't move the train any further. So we sort of limit the damage to that 10% of machines. Do you like these slides? I made that on the train last night. So we've got systems that monitor the staging phase and compare that against the rest of the fleet. And if a problem's detected, then the train stops. But it doesn't stop deploying things to the staging phase, because now what you want to do is find out what the problem is, commit the fix, and the fix will get deployed to staging. And now the system monitoring the health of the staging phase will notice that things have got better, and the train starts again. So ideally, you don't want to use this, because if something's gone out to 10% of machines, it's already done some damage. But at least we've limited the damage to 10%. OK, so the overall theme is you have the power to ship code really quickly with this system. But most of the time, you want to take it easy if you can. Do the code review, look at the experiment results, do your due diligence, make sure it's not going to cause any damage that you know about before you go ahead and commit it. That's all I have. Thank you very much.
Okay, we have some time for questions.
You've been talking about this stuff since before your company helped elect Donald Trump to the White House with an avalanche of fake news and privacy violations. So clearly, we're not doing so well, and I don't think that's because your hot swapping code isn't fast enough. So what steps are you taking to prevent that from happening again?
Yep. Good question. So lots of teams at Facebook are tackling these problems. I'm not tackling those problems personally, so I can't answer the question. Sorry.
To what extent can you inline or optimize over the shared object boundary, or is it just nothing at all?
You can definitely optimize at the bottom layer, so where the shared object is calling into libraries. You can do all of the normal cross-module inlining and cross-module optimization that happens when you're calling a library at the bottom layer. That does mean that those libraries, the libraries that you compiled the shared object against, have to be exactly the same as the ones that you compiled the server with. And that's one of the reasons that we recently worked on deterministic compilation in GHC. So when you compile things with the same flags, you're guaranteed to get the same result. So that gives you some confidence if you compile the shared object against the same set of libraries, even if they were not physically the same binary products, then it's still going to work. At the top end, that tends to be a very small API, so you don't really need to optimize across that. But you couldn't do any optimization across that. That's right.
Hello. So I'm wondering how you deal with big changes to the code that you want to hot swap, how you make sure that there are no mistakes in massive commits. Do you try to split them? Do you manage to do that always? How does it work?
I'm sorry, could you repeat the question?
Yeah,
say big changes?
you put a lot of emphasis on making extra sure that the changes won't introduce mistakes to begin with, rather than relying so much on the infrastructure to catch them all for you. So I was wondering, how do you do when you have a big change to review where it is far more difficult to find spot mistakes by reviews? Do you try to split it? How does it work in practice?
Yeah. I mean, it's definitely a difficult problem. So you make a big change. I think what you're saying is maybe the experiment results that you get back tell you that lots of things have changed, and I can't find the small problem that I really wanted to know about. That's definitely something that we're working quite hard on. Sort of extracting the signal from lots of possibly noisy experiment results is something that's definitely an active problem that we're working on. That's all I can say.
Hi. You said that the experiments thing looks really cool. You said that Sigma depends on a huge number of services, including stateful ones. How does the experiments work with the stateful backends? Like, do you have staging copies or what?
Yeah, that's a really good question. Actually, it just works against the live data. So we try our best to make things as deterministic as possible. So we've controlled very carefully all of the inputs. Sometimes we use random numbers, for example, so the random number seed is fixed. Sometimes we use caching, so we've turned off various kinds of caching. So we've made things as deterministic as possible from the input side, but we can't, obviously, we can't replicate all of the huge databases that these things are talking to, so we just have to do our best.
And so what happens if an experiment writes bad data?
The experiments don't write anything. They just return responses, and the experiment system will say if the writes change, then it will say you're writing more of this kind of thing than the old version was.
Thank you.
You've talked a lot about what you need to be able to do this, and it seems to be related to technical needs. Are you also thinking about functional IB? And if so, are there specific challenges related to that?
Could you repeat the question? I'm sorry, I didn't get the first bit.
Yeah, you've talked about how it's used for technical needs. Are there also functional needs like A/B testing? And if so, are there specific challenges related to this part?
For testing?
A/B, being able to deploy two different pieces of code and balance traffic in order to test functional outcomes.
I'm not sure I understand the question.
The question is, are you able to ship two different versions of the same code for functional reasons?
Oh, I see.
And make experiments, functional experiments for it?
Oh, I see. So you're asking if we ever want to have two versions of the code and sort of run them both for a certain amount of time in production and then compare their results.
Yeah.
We don't actually do that, but doing A/B testing is certainly a very common technique. What tends to happen in our system is that somebody will deploy both versions of the code sort of controlled by some kind of switch that they can flip via some external means. And maybe they can flip that randomly or based on some other characteristic. So that way they can do their A/B testing without having to have two versions of the code running in production. Both versions are actually running, but just compiled by a conditional.
I'm curious as to how you enforce type safety between Sigma and the external services and APIs it talks to. Like you said, code doesn't get into the repository if it doesn't type checks, but I can imagine all these external services can change without notice. So how do you deal with that?
Yeah, there's a couple of different ways. So one is we use Thrift for most of our service remote procedure calls. So Thrift is you have a language-independent specification of the protocol, and that gets compiled into your multiple languages. So as long as you ensure that you're not both talking about different versions of that protocol file, then you guarantee type safety across the boundary. The other thing is for the Facebook graph storage, the sort of main storage of user data at Facebook, there's a specification that, again, you can compile into different languages, and we compile that into Haskell types. So we guarantee that when we're talking about actual Facebook data, then we can use nice Haskell types and nice operations on that, and that's guaranteed type safe.
That was really cool, thank you. It reminds me a lot of Erlang. I was wondering, when you want to deploy a change to the more static part of the application, for example, the libraries you make available, what's the process like for that?
Yeah, that's just a normal server deployment. So you have to compile it, put it into a package, and then do a rolling deployment as you would for any other service. So we typically do that about once a week. We've been getting faster. There are sort of now automated systems that will build the code, deploy it to a few machines, do some automated testing, and sort of automate more of that process.
Final question. How often do you upgrade GHC? In which intervals? And did ever something go wrong?
Who's asking the question? I can't see.
Here.
Yes. So upgrading GHC has been a bit of a problem for us because we pre-compile all of Stackage internally, and then that's checked into a repository that we then build against internally at Facebook. And then there's lots of code that's sort of built against that. So we found that every time we have to upgrade GHC, we have to upgrade Stackage as well, and then we have to fix all of the type errors, and you have to do the whole thing in one go. So it's very difficult to do the whole process. What's more is we have a whole bunch of backported changes to our local GHC copy. So we've actually published it in the GitHub repo at our local branch of GHC. So when we move to a new version, we have to figure out which of those backported changes are now in master and which are still not, and then backport those changes again. So we're actually on 8.0 at the moment. We're in the process of upgrading to 8.2, and it's taking a while. I'm not sure if we'll be able to keep up with a new cadence of 6 monthly releases for GHC. We'll see.
Okay. I think we have to stop here because we're basically out of time. Please remain seated, but let's first thank Simon again.